Hi, my name is John Fortner, and this is my video report for Lab 4 Oscillations. Lab 4 Oscillations explores how an object suspended from a spring behaves after being released from an initial position as it is influenced by forces from the spring and gravity. And this lab relies mainly on Newton's second law, or the momentum principle, specifically the idea that the change in momentum of an object is equivalent to the net force exerted upon it. So we use the motion that we observe to calculate a changing momentum, and then use that to estimate the forces that are acting upon the object. And this lab also incorporates the energy principle, where we use our motion to sort of estimate the different energies in the system, and we can use those to visualize the conservation of energy in the system as the motion proceeds. So let's go ahead and take a look at this motion and tracker. So as you can see, the object is oscillating both up and down and left to right, which creates these two position graphs, this one being time in the y and this one being time on the x. And both of these graphs appear to sort of oscillate in position. So before we can get into building our computer model, we needed to do some calculations to find some other values related to the experiment. So here we have the period t, which I found by averaging the oscillation periods in the y direction. I got 1.519 seconds. And we can use this by rearranging this equation for period t to solve for the spring constant k sub s. And with this, plugging in our mass of 0.402 kilograms, which was given, we get a spring constant of 6.8331 newtons per meter. So here's the actual code. These are the things we calculated before. Here's where we're using the initial position to calculate L hat and S, which are used to calculate the spring force after each loop. These define the kinetic, gravitational potential, and spring potential energies, and then the total energy, which is just the sum of those different components based on the initial velocity of the object in the initial position. And here's the actual loop where the calculations take place. So here we're just defining the initial values of the energies for later when we calculate the energy change. Here we're calculating the force of gravity and the spring force, and then summing them to find the net force. Using the net force with the momentum principle, or the velocity update formula, and the position update formula to calculate the new velocity and position of the object after this loop. Here we're calculating the new L hat and S based on the change in the position. And then here we're calculating the energy changes based on the new velocity and position of the object. Here these lines we use to plot those changes in energy. And then here we're plotting the position, or the x position of the object with the time. So let's go ahead and run this computer model. So this blue ball here is the actual position as calculated by the computer model, and this red ball that flashes along is the position in tracker. And the reason this one hops along is because the time interval delta t for the red ball is smaller because our data points were further apart. This graph is the change in energy versus time, and this orange line here is our change in total energy. So the really cool thing about this graph is it demonstrates, or it proves, the conservation of energy, because this orange line is the sum of all of the energies in the system, which were kinetic energy, gravitational potential energy, and the spring potential energy. And their sum is this flat zero orange line, which goes along with what we know about the total energy, which is that it should never change as long as there's no outside force acting upon the system. And then here we have our x position of the computer model in blue versus the x position of the tracker model in red. And as you can see, there's a slight difference between the two, but they almost perfectly line up with each other and follow along really well. So that's a good sign that our model is appropriate for estimating the motion of the actual object in tracker. So finally, for the what does it mean question, here are the two periods from the x position data and the y position data. So the y position period ended up being much more accurate for determining the spring constant. And my reasoning for this is that while the x position of the object does affect the spring force because of its effect on L, because it's oscillating back and forth about evenly on the x-axis, it's affecting the spring force about the same amount when it's at either side, which means that its effect on the average spring force throughout the motion is pretty much negligible. So this is my reasoning for why the period of the y position data was much more accurate for determining the spring constant in case of S. This was Lab 4 Oscillations. Thank you for watching.